everyone. So it's my pleasure to introduce Professor Johnston from Columbia University. So she's a dynamical, she's an expert in galactic dynamics in the Milky Way and debris around the Milky Way. She got her PhD at UC Santa Cruz, then moved on to a postdoc at the Institute of Advanced Study, and assistant professor at Wellesley University, where she got an NSF Career Award. After that, she moved to Columbia University in 2006 for a professorship. And now I'm looking forward to your talk on dynamical data mining across galactic scales.
Okay, Neige, thanks very much. It's lovely to be back here in CITA again. Last time was pre-pandemic, so quite a few changes in faces since then. But it's always nice to come to Toronto. And this time I actually stayed for the weekend before. My spouse was here and we went to see the Aga Khan Museum and the Contemporary Art Museum and Kensington Market and Graffiti Alley. And we rode on the trolleys and it was great. So I've really enjoyed Toronto and now I'm enjoying my day at CITA. So dynamical data mining across the galactic scales. Broad outline of what I'm going to do very, very briefly, just to show you an example to give you context for the talk, which is the revolution from large astronomical data sets, Gaia in particular, of stars, has changed our view of the Milky Way from a quiet backwater to a not quite as quiet backwater as we thought. And this is going to motivate what we want to get to towards the end of the talk is how do we make the most of these vast data sets and the fact that the Milky Way is in a little bit of a moderate amount of disarray. In between, I'm going to do more of a deep dive into one part of those data sets to talk about what we've learned on what we've been calling microscopic scales, star by star, locally in the galaxy, of the phase-space distribution function and how that relates to macroscopic scales. So as I said, this first part, there's going to be this challenge of how we're going to make the most of our rich data sets and also look forward as motivation to the talk, the opportunities that those rich data sets afford. And what rich data sets am I talking about? We have the legacy from SDSS and photometry and their follow-up spectroscopic programs, Segway, Apogee, 2-mass spectroscopy, LaMost, RAVE, Galar. You could probably name some more. And a major one for dynamics in particular has been the Gaia survey. So for those of you who aren't Milky Way astronomers, if you've somehow escaped a Milky Way talk for the last 5 years, you may not know what Gaia is. So it's an astrometry magician. And basically, we're measuring the sky positions of 2 billion stars on the sky over the course of 5 to 10 years. And the Europeans are doing this for us, but sharing the data with us. And of course, if we do that, we can end up, if you add a radial velocity, with a full 60 phase space measure for the 2 billion stars in the galaxy that Gaia is measuring. So around the sun, and by the end of the mission, towards about half the galactic plane, we're going to have a 60 phase-space distribution function for the galaxy, which is a dynamicist's dream come true, as it were. So I'm just going to show you one plot to give you the basic picture here that illustrates what I mean when I'm saying the galaxy is in disarray. And this is just showing you here is the sun at the center of this diagram at about 8 kiloparsecs from the galactic center over here. This is data from the latest Gaia data release, which was in June this year. And what this group have done, of course, there is beautiful Gaia data release papers too, but this is a paper by Wang et al., who have taken the Gaia data and analyzed it to look at the velocity field across the face of the disk here. If you think about scale here, the galactic disk would be going around. Here's the sun, we're looking across the face, and we're looking at the mean vertical velocity in each of these little patches. And the point here simply is this mean vertical velocity is non-zero. And it's non-zero at a sort of plus or minus 10 kilometers per second scale. So it's not huge compared to the rotation speed around the galaxy, but nor is it tiny. So pre-Gaia, we only had hints of this. We had some hints pre-Gaia from those large-scale stellar surveys, which were starting to suggest this. But basically what this is giving you is this idea is not only is the galaxy on average moving around in the plane, but the stars are also wiggling the disk up and down. It's not a simple warp or an S shape either, or a flare. It is actually wiggling the disk up and down. And we can see this in radial velocity as well. So this is sort of a departure from equilibrium at an order 10% level. So when we say the Milky Way is in disarray, we mean it's departing from our beautiful equilibrium pictures of a smooth dark matter halo with a galactic disk and everything on very nearly circular orbits, equally mixed in phase. It's departing from that picture by an order of 10% level. So it's not a huge departure, but it offers many opportunities. I mean, some of the challenges are, one of the reasons we wanted to have Gaia was to build an equilibrium model of the Milky Way. And it turns out that if, and that would mean if we had an equilibrium model of the Milky Way that we could fit perfectly, we'd have a beautiful map also of the dark matter distribution underneath, for example. Now, given that the Milky Way is wobbling at the 10% level, that is limiting how well we can make these measurements. And so what that means is if we want to make really accurate measurements of the history and structure of the Milky Way and its dark matter halo, then we need to be able to model in this regime of mild disequilibrium. So it's a challenge, but at the same time, it's an opportunity. So let's talk about the opportunities. One of the opportunities, of course, so this is just illustrated by a simulation of the structure of the formation of a galaxy like the Milky Way by the FIRE team. And one of the opportunities, of course, is that we know we live in this hierarchical universe with constant interactions going on. So if we see those perturbations at the 10% level, those perturbations are a signature of interactions ongoing or in the past. And so that means there's information in the departure from equilibrium about the history of the galaxy. So that's one application we can think of. The second one is this one about dark matter itself. What we're seeing here is imagining you're taking now only the dark matter halo in a simulation, and Nico Garavito Camargo has done a visualization of the departures from perfect spherical symmetry. Let's see if we can play that again. In a simulation of a single satellite, this is the edge of the satellite here, interacting with a galaxy that you can't see at the center here. And it's these are departures, I've said spherical, it's probably ellipsoidal symmetry in that simulation at the end of this. And you can see these huge perturbations, again, at the sort of 10% level to the dark matter halo in this simulation. So it turns out that some of the departures from equilibrium that we're seeing more in the halo than in the disk of the Milky Way, we can start attributing to large-scale asymmetries in the dark matter halo. So on the one hand, we thought we were going to be able to, at least I thought we were going to be able to measure the triaxiality of our galaxy, our galactic halo, as a function of radius, and maybe even measure the orientation as a function of radius. And it turns out that that's almost a silly question when you look at the face of, sorry, let me go forward. When you look at this sort of visualization of what we think the dark matter halo of the Milky Way might look like only in the case of a single satellite perturbing it. So again, this seems like a challenge, but at the same time, it's an opportunity because it is rather thrilling, honestly. It hadn't occurred to me that we could be measuring or finding signatures of the wake of the LMC in our own dark matter halo. And that is actually what we're starting to think that we'll be able to do with these departures from equilibrium. Okay, the other thing that's a dynamicist dream again is dynamical mechanisms. The idea that these departures from equilibrium here, well, what we're actually seeing here, this density here, is the wake in the dark matter halo that's being induced by the infall of the LMC. And it's this dark matter wake that is going to create the dynamical effect of dynamical friction on the LMC, for instance. So by being able to study these things, we're actually going to be able to directly measure some of the things that we've spent decades reading about in Binney and Tremaine and trying to understand from a theoretical perspective. We're actually going to be able to look and pick apart some of these mechanisms. So external and internal and intra-component couplings, the coupling between the LMC and the dark matter halo, the coupling between the dark matter halo and the disk, the back reaction of the disk on the LMC's orbit, etc. These are actual things we should be able to pick apart with the level of detail that we've got in the Milky Way. So the Milky Way disk isn't this smooth disk with mean z at a single in a zero plane. It's rippling up and down, but that rippling up and down is probably containing signatures of all these effects going on at once. The other thing we might hope to do is actually look at the fundamental modes in the dark matter halo, phase mixing signatures in the disk, and processes such as dynamical as relaxation. So in other words, we're taking all the terminology in Binney and Tremaine, and we're actually going to try and find it in our own galaxy. So in some ways, right, the history of the Milky Way and dark matter, for me, for a long time, have been a motivation for studying the Milky Way, because we may be able to study that in much more detail than elsewhere in the universe. But actually, what this has turned into, now that we understand that we're in this near equilibrium position, is to understand these dynamical mechanisms and actually learn about dynamics at a very fundamental and deep way using the data set, which will then be able to go back and feed into these things. That's what we're aiming to do. Okay, so in this talk, what I'm hoping to do is two things. As I said, we're going to look, first of all, at this example of a relationship between local and global disturbances in the Milky Way, just to give you a sense of how rich the data set is, and also because this is a major thrust in the research that I'm thinking about these days. And then what I think the last part of the talk is the dynamical data mining. And this is introducing a set of tools for looking at data sets, whether they're simulated or observed, and to explore them and make connections and communication between different components of your data sets, but also between these different ways of studying data sets. And hopefully this is going to make sense by the end of the talk. So let's start with this microscopic to macroscopic view of the disk in particular of the Milky Way, with reference in particular to this wobbling up and down, which is just one of the signatures of disequilibrium that Gaia has uncovered, or if not uncovered, made extremely clear and created beautiful maps of. To do this, let's start by just talking about orbits in the galactic disk to get ourselves oriented. And I actually spent most of my career thinking about the halo and orbits in the halo and disruptions of satellites. So the disk has been something I've been working on just the last 5 to 10 years. So I always like to think about the orbital properties before putting them together to think about dynamics. And there's a beautiful illustration in Wilma Trick's PhD thesis that illustrates this. So she's showing just I think 3 different orbits here in the XY plane. And you can see in general, these orbits are nearly circular. If we're talking about disk orbits, things go round and round in a circle about 200 kilometers per second. And we're going to do a lot of phase space plots, different projections. So here's our first phase space plot. If we plot X versus VX instead of X versus Y, you'll see that in this projection, these orbits project to a circle also. So as you go negative, you're traveling in a negative direction in X from positive to negative, then you've got a negative VX. And when you're going to negative to positive, you've got a positive VX. And this pattern is going to come back again and again. If we look a little more closely here, you can see that these Wilma has chosen to plot 3 different orbits here. The red one almost exactly circular. The blue one is oscillating in and out in radius slightly, and the green one is oscillating further in and out in radius. So we can think about this as all of these orbits having the same parent orbit. So this is in the epicyclic approximation. We can think of all of these orbits as basically going around the galaxy. The red one would go almost exactly along this line. The blue one would have a guiding center that moved along the black line, but would perform a small epicycle in radius going towards the center and out away from the center as it goes around the galaxy. And the green one would have a larger epicycle, right? So if we project this into a phase space diagram, in this case, we can look at the radius explored by the red, blue, and green orbits and the radial velocity. And you get the same pattern here, that each of these orbits, when projected into this one dimension of phase space, well, 2 dimensions of phase space, again, you see circles, right? So we've got so far orbits in the disk go round and round, they oscillate in and out, and they oscillate up and down. We can do the same thing by looking at these orbits edge on, and this is R versus Z, and Wilmer's chosen orbits. The green one is going in and out, but it's exactly in the plane. The red one has no radial motion, it's going almost vertically up and down, and the blue one is filling a little box as it goes around the galaxy. And once again, you can make a phase space projection of these orbits, okay? So overall, we've got these orbits, stars and galaxies go round and round, up and down, and in and out. That's the motion in the disk. Now we're going to talk about the consequence of those motions, which is just very simple, or thinking about orbits in terms of data. And the last thing to add to this before we get there is to remind ourselves that, of course, these have their own specific frequencies. So the longest period is going around the galaxy, and then you have shorter periods for stars going up and down. And so that is an equivalent to, for a star going up and down, is going once around in this diagram. And the stars in the center with low, we'd say low vertical axiom, but with small oscillations vertically, go round faster than the ones further out. Okay. So going on, let's think about the actual data now, and we'll talk about the up and down motion first. And so what I'm going to show you is a plot of nearby Gaia data from Gaia DR2. It contains about 7 million stars, and we're just going to plot in this about a kiloparsec volume around the sun, a little bit less. We're just going to plot the vertical position above and below the plane of the galaxy, and the vertical motion going up and down of those stars. And to remind you, what we see here, or rather, what we expect here is the orbits just fill these circles. So pre-Gaia DR2, we expected this to be a simple, maybe Gaussian distribution, falling densest at the center where the galactic plane is densest and falling off in all directions. But you probably know this because there's an expert in the room sitting right here, that what was actually found in the Gaia data was this. And this was first plotted by Teresa Antoja on the Gaia DR2 release day. We saw it the next day in Astro PH paper, and I think this is many people's favorite result from Gaia DR2. And this is basically that you see when you make this plot, what should be a random sample, a non-random distribution. In this case, it's color-coded by phi velocity, but you can also look at just density contours here. You can look at metallicity. Neige is doing this now. And you still see this beautiful snail-like pattern. And this is, again, a signature of departure from equilibrium. So in equilibrium, we should just see a sort of Gaussian ball, basically. And the snail is a signature that something happened in the galaxy not so long ago. I mean, essentially what you're seeing, oh, sorry, let me go backwards. Essentially what you're seeing is that something happened in the galaxy not so long ago that offset the beautiful, smooth Gaussian ball that should be here, offset it. And then the orbits of the stars are moving faster in the center than the outside. And this is a signature of a perturbed distribution phase mixing in time. So this is phase mixing being visualized in real data. And the beautiful thing about this is it's still true that the data has higher resolution than any of the simulations that have yet been run. So, but to put this in scale, this is what I'm calling the microscopic view. On the macroscopic view, I've already told you the galaxy is going up and down. The galaxy going up and down, if we averaged the data here in Z, you would find a mean offset in Z. if you averaged it in VZ, this whole data, just summed it up in VZ, you'd find a mean offset in VZ. So this is the full phase space signature of what we can see on the macroscopic scales of a mean offset in Z and VZ. Are there any questions here? People happy with this? Yay, so let's just zip along. So we talked about phase mixing. This is phase mixing. The last one was phase mixing of an offset distribution, which is oscillating up and down, with the stars close to the disk oscillating up and down faster than the stars further away. But the other thing, so sorry, I meant to take this out. Imagine this is animated. This is completely blank. Do not look here, right? If you look at stars today and you say they're in a volume around the sun, this black, blue, and red star, say these are the stars that you plotted in your ZVZ plane. Because we know that stars around the galaxy move on near circular orbits, we can represent the orbit of the black star, the red star, and the blue star in terms of a guiding center and the epicycle that we talked about just a few slides back. So it's actually true that a local volume around the sun like this will contain stars that remain always within the volume as the guiding center moves around the galaxy. But the stars, that's also going to contain stars that are sometimes within the same volume as the black star and sometimes not within the same volume as the black star. So this star, for instance, had a guiding center for its epicyclic orbit that is closer to the galactic center, and this star has a guiding center that's further away. So this star is near a pericenter, this star is near an apocenter. When you start thinking about that, then that allows us to start thinking about what information is contained in this little patch here. Like I've told you, it's a signature of some interaction that's happened in the past. But what you actually see when you look at these boxes here, the stars that have guiding centers within this box, we'll color code those with black. That in this box today, this is X, Y in the galaxy, at some time in the past, this is where the stars in black may have come from. If we look at the stars in red that are currently inside this box, but have guiding centers outside the box towards the center of the galaxy, they would actually have come from a systematically different place in the galaxy some time ago. And if we look at the stars that are blue, the stars that are currently in this box, but at some time in the past were not part of the box, they have guiding centers outside, they would be in a systematically different place in the past. So this is today, all these stars are in the same box, but in the past, the blue stars, the black stars, and the red stars were in systematically different places in the galaxy. So when I say this, the stars that make up the spiral were offset by something in the past, then it's actually possible that the blue stars were offset differently than the black stars, and they were offset differently from the red stars during that interaction. So this is to give you a sense of how much information that could possibly be contained even within this local volume of the galaxy. So what we're going to do now is take that same data. Before we plotted all 7 million stars from here in one ZVZ plane, and we found a beautiful phase spiral. What I'm going to show you next is an updated version of that plot. And in the updated version, we're going to take the stars in here and we're going to project them into different boxes of different guiding radii. Red is closest to the galactic center, blue is further from the galactic center, rather than their current position. And we can also play this game in angle. We can actually think of guiding center radii that are, sorry, down here, ahead of the rotation of the sun and behind the rotation of the sun. And what we're going to do this with is Gaia DR3 data, which actually has many more stars. So Jason Hunt made this plot on the day that Gaia DR3 was released. And this is a plot where in terms of, here we go, guiding center radius. So the sun sits at about 8 kiloparsecs. This would be stars with guiding in the current volume around the sun, but with guiding center radii that are out to 10 kpc. And these are stars that are currently within the same volume as the sun, but their guiding center radius would put them mostly at a radius of about 6 kpc. And then these are looking ahead of galactic rotation and behind galactic rotation. And so towards the center, you can imagine these are the stars that sit close to the solar volume now and in the future and in the past, etc. And if we just look at one row here, what you're supposed to see, I hope you can see, is that these spirals are not all the same. As you go outwards and as you go inwards, the phase of the spiral and the number of wraps you can see is systematically different. And the same if you go up and down. In particular, a major result that Jason found. Oh, Jason was the postdoc here, and he was the one who told me what to do this weekend in Toronto, by the way. As a major result that Jason found is as you go towards the galactic center, you go from seeing a one-arm spiral to a two-arm spiral, which is really fun. So what's actually going on there? Sorry, I didn't put a slide in on this, but we can do a visual. I've got a visual aid here. So I talked about the galactic disk being pushed up and down. This is an m=1 in ZVZ mode, right? It's a single arm spiral because you're just going up together and down together and it's wrapping once. And this is called a bending mode. So fellow Canadian Larry Widrow has written a lot of papers on this. So go and read his papers because he taught me everything I knew about this. But the other thing Larry taught me was the other thing that you can set up is what's called a breathing mode. So a breathing mode would be the galaxy is breathing. It's like it's doing yoga. It's going, right? And that's actually a two-arm spiral mode. So if you offset, then you end up with a one-arm spiral. That's an up and down motion. If you squash the galactic disk, then this is a two-arm spiral. You're actually going systematically up and down as the whole disk, but it comes out as a two-arm spiral. Whether you get a one-arm spiral or two-arm spiral really has to do with the nature of your interaction. So a one-arm spiral is when the interaction is slow. No, wait a minute. Let me get this the right way around. Yes, slow relative to the stars going up and down, so that it gets to pull the whole of the disk up and down. A breathing mode is when the object or whatever interaction appears very suddenly and suddenly squashes the disk so that it makes it breathe. So it has to do with the nature of the interaction and the relative to the local oscillations in your disk. Okay, but this is really fun because as we're looking here, we're seeing fundamental dynamics at different radii in the disk. Ting, you had a question. Here. Sorry, this version of the talk, I didn't blow this up, but there's one here, one here. These are the clearest ones. In the galaxy, yeah. Okay, so the main point here is there's a lot of information here. The community has had a wild time. If I go backwards, let me see. Oh, sorry. I just tried to write down a few of the references here, but in particular, in the last 2 months, a lot of us have been publishing on this. Here's a local heroine and a local hero, and Jason was here too, so he's sort of local as well, right? But so there's we're having a lot of fun with this data. Why? Well, intuitively, you can imagine that this windingness, right? These spirals get tighter and tighter over time. So they're actually a clock. So you can actually read off, once you know the local frequency distribution, you can make up a time. How long would it take for this spiral to unwind and return to being its initial state of just a blob? So we can read off different times all the way across this plane. So I'm not going to do much more on this, but just to give you a teaser, this is some of the work that we did in our group, led by Elise Daraford, who's a graduate student at Stanford. This is a nice equivalent plot from NAIJ right here. But let me explain this one. This one is actually showing in each of these boxes here, we've taken stars in this neighborhood in angular momentum, but this corresponds to the inner galaxy and the outer galaxy in terms of guiding radius. And these correspond to the angle ahead of galactic rotation and behind. So it's really, equivalently, what we've done is for each of these boxes, we've unwound the spiral and asked when was the interaction, right? And what you're supposed to see here is the main take home here is you can see systematic regions, right? The interaction time here is different from the interaction time here, is different from the interaction time here. And this is getting at the idea that by taking this local data, remember this is all within 1 kpc of the sun, remembering that those data in the past were in different parts of the disk, you may actually be learning about several different interactions, or it might actually be all the same interaction, but viewed from different perspectives. But the key point here is not the answer. I think Nej would agree. None of us know what the answer of what the interaction was, but we do know there's a lot of information there that we're going to be taking quite a few more years to unpack. Okay, so the key point here is we've got the Milky Way under a microscope. That microscopic behavior is from macroscopic interactions and has macroscopic consequences. And to really interpret it really messes with your mind, right, Nej? Yes, really messes with your mind. Okay, questions?
Just a technical.
Yeah.
How do you get the action?
So this is just the angular momentum. This is easy.
Oh,
That's part easy. Exactly. So the JZ and the JR, right? So Nej actually did a beautiful plot, same idea, but here she's plotting J phi. You should give the rest of the talk. She's plotting J phi as we are, which is just angular momentum, and she is plotting JR. And here, each of the boxes is saying, let's split the data in J phi and JR, radial action, less eccentric orbits, more eccentric orbits. And the way we're getting JR and JZ is just assuming a potential model. So the other game that we're all playing is, of course, if you get the potential model wrong, then your projections are wrong. So actually, to make this plot, great question. You notice how circular these plots are? That's telling us we have a reasonable potential model here. We didn't start there. So actually, in the appendix of this paper, we have to adjust our potential parameters in order to make this plot. Sorry, I didn't say that. This is not exactly that plot. I am confusing you guys. Yes, but I'm answering your question, but with the wrong plot. Okay, sorry. So ignore that part for a second. Okay. So, but I have to show you this. Okay. This is start. Okay. Yeah. Okay, this is really fun. This is what we call locally, we call this the crazy Jason plot. This is Jason, a picture of, no, it's Jason simulation, 2 billion particle simulation, several hundred million particles in the disk. And here, every little box here is looking at the simulation face down, and he's making a little ZVZ diagram face down. And what you can see over time is in our simulation here, you create spirals across microscopic spirals. But the other point you're supposed to see is this macroscopic thing. Though the shapes of those spirals, this is back to the beginning of the simulation, the shapes of the microscopic spirals are correlated. That's why our eyes are great correlation machines. We can see macroscopic spirals, correlations between the microscopic spirals across the face of the disk. And this has something to do with the fact that local areas of the disk will phase mix around the disk over time. So we've got phase mixing in ZVZ locally, but the different groups are spreading around the disk, even though they start at the top over time. And that's why you see the macroscopic spirals at the same time. So actually, I meant to show you this before I said, this can really make your mind hurt, right? How do you deal with this? There's an immense amount of information here. And if we can correlate the macroscopic with the microscopic, we should be able to tease it out and come up with real answers to our 10% disequilibrium of the Milky Way. But how are we going to do that? Okay, so the last part of the talk, what I want to do is talk about what we're naming dynamical data mining. And this was really motivated by all the different ways of studying dynamics, whether you want to write down a linear perturbation analysis using the collisionless Boltzmann equation and starting from that, or run simulations, or go and link at observations, or take a purely data-driven approach. The data-driven approach is really about feature discovery and characterization. And the theory approach is really about dynamical interpretation. But what we really want to do is both things at once, right? Okay, So let's take an example. What I'm going to do for the rest of the talk is talk about simulations, and we're just going to talk about feature discovery and dynamical interpretation of simulations. And we're starting from one of my favorite simulations, because Shervin Laporte ran this while he was at Columbia, and it's of a satellite interacting with the Milky Way. And I want you to remember what we talked about at the beginning. This system has a satellite with its own dark matter halo. It has a dark matter halo that you can't see here, but the satellite is distorting, and it has a disk component, and everything's interacting with everything else. So you have the satellite coming in, distorting the dark matter halo. In fact, let's run that one more time. The satellite's going to come in, it's going to distort the dark matter halo. The satellite itself, you can see its imprint on the disk, but the dark matter halo will also imprint on the disk. So as the satellite comes back, you'll see it slam through the disk a second time, and then a third time, and you can really see those vertical oscillations going on, as well as internal oscillations. The name of the game, we think this is going on in the Milky Way. How do we untangle this all in order to get to fundamental stories about history, dynamics, and the nature of dark matter? So a standard way of looking at simulations, and indeed I'm on this paper too, Eloisa Poggio did this beautiful analysis. We looked at the surface density of our disk here at different times in the simulation. And what we did was a Fourier analysis. So first of all, here's the surface density. We can look at the Z oscillations, and one way of looking at simulations is just to make visualizations like this, so we can see oscillations below and above the plane at these different times, and we can see how they increase over time. To quantify this, we decided to do a Fourier analysis. So this is the first part of trying to go from looking at a simulation and describing it in general by taking averages, etc. The first thing you might try to do is do a basis function expansion. And so what we did in Eloisa's paper is take each snapshot that might look like this in terms of mean VZ and decompose it in terms of m equals 0, 1, and 2 modes. The plus signs have gone off. This should be over here. So this mean VZZ can be think of a superposition of rings going up and down in the disk. We look at the average up or down motion in a ring here, and that's what's being plotted. Here we're looking at a Fourier transform of each annulus and looking at the phase and amplitude of the Z component in each annulus. And here we're doing the m equals 2 component. So in other words, these three separate components add up to the mean Z at every annulus and each time. And we can compress the full data set into a finite set of coefficients. T would be each snapshot, and we would have maybe 10 annuli with, we'd look at we'd make 30 numbers here to characterize the full surface density distribution. It's just Fourier transforms on annuli. It's a basic basis function expansion, right? More generally, let's just do this. So that means we can look at the entire simulation. Instead of me showing you a movie, I can show you something more quantitative in a single plot. So this is as a function of radius and time. So these are snapshots. This is the inner disk and the outer disk. And all we've done here is plot what is the dominant mode at different times. These vertical lines represent disk crossings of the satellite. And it's kind of fun to see how each disk crossing seems to reset patterns here. I don't want you to take this all in, right? The point is we're trying to summarize in a compact way a complex simulation. Ting, go ahead. No, now is over here. Yeah, this is when the disk is isolated and the satellite's falling in from the virial radius. Yeah. So this is basis function expansions. We did Fourier transforms on radii, annuli radii. More generally, you can actually write these as coefficients of some basis function expansions in radii and azimuth, or for ellipsoidal expansions, it could be density, basis function expansions in radius and spherical harmonics, right? I mean, this sort of description is used throughout astronomy, and it's used to connect theory, observations, and data. Simulations, observations, and data, theory, simulations, observations, and data. The classic example would be power spectrum of the cosmic microwave background. That there you take an expansion in spherical harmonics and you can predict that in linear theory, you can have it in simulations, and you can look at it in data. So this is a language that is used in other branches of astronomy and in physics in general, right? Handy. Okay, so the BFE vocabulary provides us a compact summary of features. Sorry, I missed one thing. I missed a slide. Here we go. The great thing is this is compact. It's flexible. It allows you to describe things, deviations from spherical symmetry, and it picks out large-scale features, which are the things we tend to be most interested in. As I said, it can be used to connect across the different ways of studying things in astronomy. And lastly, for dynamicists, if we really want to study density, we can also do this with velocity and other dimensions. But if we want to study density, we can choose basis function expansions that are solutions of Poisson's equations. And that actually makes them dynamically meaningful, these coefficients in particular, dynamically meaningful. So this is why we call this dynamical data mining. So maybe the more interesting part, this should be somewhat familiar from other fields and from dynamics itself. The more important part, a more fundamental part, is how do we go from characterizing these features, making that plot that I showed you, which compresses a lot of data into a smaller amount of data, but it doesn't really tell you what dynamical processes are acting. How do we do that? And what I want to present to you is multi-channel singular spectrum analysis. This is my first attempt to describe this technically, so please ask questions as we go along. The idea for this comes from, I think it's engineering, fluids in particular, and it's brought to us courtesy of Martin Weinberg and Mike Peterson, who've been using this for a couple of years. The basic idea is you have a set of basis functions, right? You run your simulation, you extract a set of basis functions. Let's say they represent the density field. So you've got 100 numbers maybe, which represents this density field at maybe 1,000 time steps. And this is going to be, this red bar represents your entire time series of data. So your coefficients at time 1 up to your coefficients at time n. So what multi-channel singular spectrum analysis does is it makes a filter out of the data itself. So let's take the first K snapshots and the series of coefficients here. And what we do is we take those first K snapshot coefficients and we line them up in different lagged sequences, all of the same length. And we compare what we see in our filter with what we see in the lagged sequence. So if the lagged sequence matches your filter, you're going to get a high number. If your lagged sequence does not match your filter, if they're not coherent, you'll get a low signal, right? You're doing a sort of covariance analysis in this sense. And the nice thing is you're doing it with a filter or you could think of it as a matched filter technique, but you're using a filter that's not a function, it's actually your data itself, okay? So here we are, we're going along our full time sequence with a subsequence systematically to find the matches. And what you do in essence, first of all, it's obvious, I hope, that you can find correlations across time. If you had a purely sinusoidal signal here, every time you went one period further, we're going to be another 10 minutes. We'll get there. Thank you very much. Every time you went one period further, you would get a positive correlation, just a Fourier transform. But the nice thing here is this does not have to be sinusoidal. And the second nice thing is because you're also matching the actual coefficients, you're actually finding correlations in space as well. So if you have a feature that picks out certain coefficients, you'll be matching those coefficients in space and across time, if that's making sense. So it returns repeating patterns or trends as principal components. Underneath the hood, you can think of this as a principal component analysis, or in linear algebra as a singular value decomposition question.
Yeah, I was going to ask, like, are you assuming some sort of linear component in how you construct the filter, like the things that are on the top row evolve linearly to the others?
You're just comparing data with data, so you're not specifying a function at all. You're just specifying a time series and comparing it. Is that making sense?
Yeah, my question is, like, so you're looking for a time here for data and a compare to itself, right?
Yes.
Are you, in the way that the filter is construct it, are you assuming that like the pose that it's shifting?
Yes, exactly.
Right, so it's not, it's gonna be like a linear.
Yeah. Yes, you're exactly right. Yep.
What about if there's like a lot of noise corrupting what
Yeah.
you have in your data and start trying to
Yeah. Yeah. No, yeah, exactly. You will correlate noise, but noise is noise. I'll show you. So that means it, right. In fact, what you'll find is because the noise doesn't have the coherent pattern, it will try and correlate it. So this is not, I should have said this at the beginning, this is not an unsupervised learning technique. It's a technique then you need to learn from it, which I'll demonstrate going forward. So to answer that question, here's a simple 1D model from Mike Peterson, which is showing you amplitude versus sample number of a signal where you've got some noise, it's periodic and it's growing. When you apply this method, you can pull out separately as separate PCs, the growing trend and the periodic signal and the noise. It separates all of them. And the noise can actually be higher than the signal, but because it's not correlated, it will be pulled out as lower order PCs, not the high order PCs. Now, to finish off today, what I want to do is show you, okay, an example. And the example I'm going to show you is incredibly boring because it's an isolated simulation. Let's see, maybe I have to click over here. It's just a simulation of an equilibrium disk, bulge, and halo model. So here, the main thing, you don't see anything because the main thing here is numerical noise. Otherwise, it's constructed to be an equilibrium. So, and we wanted to know what can we see when we perform this analysis on this. And this was work led by Alex Johnston, who is just a postbac at the time, and is now a grad student at Harvard. So we look at our really boring simulation. The basis function expansion view, let's look at the m equals 0. So spherically the disk, the azimuthally symmetric coefficients, and the ends are the different orders in radius of your basis function. And the point here is you do see some non-equilibrium at the beginning that quickly damps. This is the monopole, this is the dipole, the m equals 1 and the m equals 2. And you can see that these bottom ones in particular are noise dominated. So when we put all these coefficients into this machinery, remember this is what we see for the raw coefficients, and it separates them into these PC groups. So what you should see here, is it starting? No. Okay, I'll just play it over here. What you should see here is a relatively slow-paced evolution. Here you saw a rapid evolution early on in the simulation. So this is a relatively slow-paced evolution that gradually damps down. In the middle, you should have seen a rapid evolution. On the edge, you just see up and down oscillations all the way along. So I'll show you this graphically, but what we're seeing here, long pace, did I miss it already? No, we got to pull it backwards. Okay, we're doing this together, the audience and I. Okay. Okay, let's play it one more time. Boom. So you sort of blink and miss it here. Here is a long evolution that gradually damps, and this is nurdling along. So what you're going to see, just to give you a sense of where you go from here, answering this question about to get at this point of physical interpretation that this is not unsupervised learning. This is now, if we add BFE and MSSA, we look at M equals naught and the first two PCs, which is the first group of PCs. You can see in the disk, you see some amplitude. This is about 2% deviations that slowly damp over time. So this is the amplitude of the coefficients that contribute to this PC. This is a Fourier transform. This is showing that you have very low of this signal, have very low frequency oscillations here. And the fun thing is we can also do this for the halo. So this is the disk and this is the halo. And you can see for the halo, the one and two PC has similar characteristics here of a largest oscillation, actually at a higher level, 4% level, that decays over time, but it also has very low frequency. So if I try and interpret this, the first thing are these mild oscillations at the beginning that decay, that are common in the halo and the disk. and they're actually higher in the halo. The second thing is that you have very low frequency oscillations. The time period here is not characteristic of the disk, because this is less than 1 oscillation per gigayear. This is more characteristic of the halo. And the third thing to see is the many frequencies are excited, not a single frequency. Our interpretation, I'm sorry, the last thing is you have the same sort of frequency distribution in the disk and the halo. Our interpretation of this is that you're starting your equilibrium initial conditions, but actually the disk and the halo are slightly adjusting to each other, because it's very hard to start a disk and halo in exact equilibrium. So the halo is slightly contracting and expanding very slowly, and the disk is responding to that. That's what we're seeing at a below 1% level. So I'm going to go through the rest in less detail because we're running out of time, but also it's kind of interesting, but kind of boring if I talk through every single slide with you. The physical interpretation of the disk plus halo next to coefficients is that you can see that what we've pulled out here is the ringing of the disk early on, which is again that the disk is out of equilibrium and it rings and settles down. There's less of a coupling to the halo in this one. So we think of this as really more like phase mixing of the disk. So another fundamental dynamical term here. And I want to show you, here is the higher order PCs, which have very little signal, but look at their frequency distribution, it's flat. So this is basically noise. We've separated the noise, even though the noise is actually at a higher level than the signal in this case. I want to show you one more example from m=1, because this is actually Martin Weinberg's favorite example, so I have to show it to you. So if I play you this one, so this is for the m=1, I can play the same thing. What do we see? These we think are noise again. However, you see the first couple of groups of PCs are very, very, very slow retrograde spiral, one-arm spiral, and a slightly faster retrograde one-arm spiral. Again, at a very, very low level. Look at the level of the noise here. What we think this is, if we play this with the halo at the same time, we think what we're seeing, again, is coupling between the disk and the halo. But notice the halo, especially in this first PC, is stronger than the disk. Martin's really excited about this because he's been working for decades on dark matter halos, their distribution, and how they're actually unstable to m=1 mode. Even if they're sitting by themselves, they will secularly grow an m=1 mode. So what he thinks is happening here is we've constructed an NFW halo. It's unstable. It's a generic property of dark matter halos in simulations, in theory, probably in the real universe. So it's growing its own unstable m=1 mode, and it's exciting that in the disk. So that's really fun because this is about fundamental dynamics. Okay, so summary. The thing here is that I want you to take away is not, this is how things behave necessarily, but that we're identifying different dynamical mechanisms and separating from noise in a simulation here. And we're doing this automatically. It is supervised. You saw what I had to go through to explain our interpretation, but it allows us to have a deep dive into the simulation that would be impossible without the MSSA component here. We can't do it alone. And what I want to finish up with is prospects for this. I hope you're convinced this is a wonderful dynamical discovery machine. The things that we're working on now, these are 4 different projects we have going, led by these postdocs and graduate students. And of course, Nico Garavito Camargo really wants to think about wakes in dark matter halos. But we can think about, Jason is looking at disk bulge halo satellite interactions, and Arpit and Silvio looking at this in a cosmological context, because of course we can do this with cosmological simulations as well, and looking at larger samples. Let me see. Chris Hamilton works on linear theory, so he's excited more about the things that Martin gets excited about, which is you do a linear perturbation theory analysis of the collisionless Boltzmann equation and then compare to simulations. What else do we have? Mike Peterson, remembering this plot from early on where we're looking VZ in our galaxy. Well, manga data for other galaxies has beautiful maps like this, and we could think about what that means for external galaxies. And lastly, back to where we started from, this micro-macro project. the one that I'm really keen on working on, and Adrian Price-Whelan and Jason Hunt and David Hogg, led by graduate student Kian Tavanger. So Kian is trying to do a basis function expansion of the micro snails and then correlate them across the face of the disk using MSSA to try and understand how these micro snails spread across the disk and dynamical connections there. Okay, so I'll leave you with the crazy Jason playing, and that's everything I wanted to say.
So thank you, Kathryn, for this beautiful talk. I'm going to ask if there are any questions from the in-person audience or the online audience. Yep.
So you know that the M=1 grid mode that
Yes. Yes.
you did a simulation in the presence of the disk. So does the presence of this kind of ignite?
Yeah, I think that's an interesting question. It would be nice if Martin was here to answer that question. I mean, my sense in general, it could be that actually triggered it, but I guess what he's trying to say is anything could be the trigger, and that this is generic to the types of distributions, spherical symmetric distributions that are increasing towards the center. So he would say that what we're uncovering here is something that generically should be happening in the universe. And when we see M=1 modes in disks, they're not all going to be due to this, but some of them could be as simple as secular evolution of the halo. And for the first time, we've been able to actually see that process in a simulation and capture it. Yeah.
Thank you.
First, very nice talk. So if we look at like a galactic astronomy textbooks, right, will tell you that the Milky Way disk has warp. And I'm wondering, now that we have all these Gaia 2 results, can you confidently say all the warps that we are talking about, like back 50 years ago, is actually basically this phase space spiral? It's the same thing, just microscopic versus macroscopic. And another question is whether this whole thing we are seeing here, either it's called a phase space spiral or the warp, is a consequence of like it's consequence of ELB seeing for Sag info or Gaia info. Like do we all combination of them? Can we tell like which one is dominating?
Yeah, so I think that the answer to your second question is the point of this. I think the answer to your second question currently is no. We can't tell what it is, because it's you mentioned it is of Gaia Enceladus, is it the LMC? But actually, any of those, Gaia Enceladus falls in, it excites a wake in the dark matter halo, it sets the disk rippling. The wake in the dark matter halo can set off snails. The ripple in the disk can set off snails. So that actually means the waters become very murky in distinguishing which of those it could be. And I think the best way to be able to distinguish it will be to understand how these snails are correlated on larger scales, to understand where the perturbation is coming from, right? So that's the answer to your second question. Your first question was the warp. Oh, yeah. So I think, yes, that wherever you look, you'll as any vertical perturbation will, so long as you have different timescales, will mix and you'll see a snail. It may be too faint for you to find, but you'll see one, if that makes sense. Then, so it's not that they're different. They're different projections of the same thing, same phenomenon.
But they come from the same people or
Right. I think that's let's discuss that one over dinner. Yeah, I don't want to give a trite answer to that. Yeah.
So I had two questions. One is going from being unstable to an M=1 mode.
Yeah.
How come in the original NFW simulations, they didn't see an n=1. What is that? They didn't have good enough resolution, or do you know what's going on?
Yeah, no, that's an interesting question. I mean, there is the resolution question, but there is also this is a subtle effect that we've got here. This is 4% effect, right? So it's resolution to resolve the mode, it's dynamically, but then it's also resolution to actually see it when you do your analysis, right? And I'm not sure if people did analyses of looking for m=1, so which is a different question, right? And lastly, of course, the universe in those cosmological simulations, there are constant interactions. So how important is it? I'm not sure we know at this point.
The other thing is so he's done in linear stability analysis.
Yes.
Presumably he's never tried to figure out what it saturates at or how long it grows.
I am not sure. I think my memory is it's going to take the age of the universe to saturate, right? One thing I didn't show you, so now I didn't show you I didn't point out carefully the difference in character here because I wanted to get to the end. But remember, I was pointing out for the earlier modes, you had a spread in frequencies. When you look at the m=1, you see a single well-defined frequency, and this is a signature exactly of this being a fundamental mode with a single frequency. But you can actually look in the simulation. You can see the growing. This will capture the growing. It will capture the saturation. In fact, you can almost see that it's saturating at that point. So it is something we will be able to measure in the simulations, and if they haven't done it, like compared to theory or predict it in the simulations as well.
Let me ask a more fundamental sort of mathematical question, right?
Yeah.
You're expanding in Fourier transforms in phi's, but you did mention you could do elliptical basis functions for elliptical potentials.
Yes, yes.
Because that seems like the better way to do it. If the modes,
yes,
you're going to capture the modes better.
Yes. So for the halo, we are doing a spherical harmonics. This is just for the disk.
Right.
And I just have this illustrated in the disk. So what we do to relate the disk and the halo is we look at the projection down to the L=1 for the m=1, the L=0 for the m=0. But yeah, we do the halo in the spherical harmonics. Yeah, so that you can actually use the exact same expansion for your linear theory and your simulation at the same time.
And since it is pretty linear, I mean, 4% is pretty small.
Yeah.
Right. In principle, you should be able to back out different collisions or mergers.
Yes, no, so this is an isolated simulation for the Milky Way. Yeah, the Milky Way is more, I would say, about 10% level. To what extent we'll be able to do that, I don't know. I think the complication is the fact that many things are happening at once, because it's not because as I said before, you've got the disk, the halo, and the satellite that are all coupling.
Let me give you why I think you might be able to do better than that. If you look at global circulation models of the Earth,
Yes.
they have, of course, hundreds or thousands of normal modes.
Yes.
People have now we've got detectors around the planet, but not
Yes.
that many. You've got more detectors around the galaxy than we do around the planet.
Yes.
And you can see the signatures of dozens, if not hundreds, of normal modes, their amplitude, their phase. And you can actually work out in many cases what's driving them. So in principle, you could do the same thing with the Gaia data.
Okay. Okay. So you're a convert. See, you want us to do this.
Well, I want you to do the same sort of. Have you tried making a dispersion relation between K and omega for your different modes?
No.
Okay, good.
Are there more questions in person or from the online audience? Okay, if not, Sam.
This is perhaps a bit open-ended, but you mentioned all these Gaia sort of from equilibrium at about the 10% level. And in that fire snapshot, for example, it definitely looked like there were moments that are well above 10%. So is it just our good fortune that we're at the 10% level that we can do anything with this, or?
It's an interesting question. I mean, we have a major merger about to happen with the LMC. There, we had a major merger a few giga-years ago, maybe 5 to 7 giga-years ago, with Gaia and Cedulus sausage. Sagittarius is minor-ish. When I say major, I mean major, minor, major, not major, major, like not 1-to-1. So I think we are in this sort of quietish few years, but it's never completely quiet. It's less quiet than we supposed, but it's not at the level of violent relaxation. It's the level of some relaxation, but not violent. Okay.
Before we thank Kathryn, I wanted to advertise for our talk tomorrow. So today we enjoyed dynamics in the Milky Way, and tomorrow Kathryn is giving a talk about dynamics in academia that's related to diversity and inclusion. Okay, at 10:30 here.
Yeah. So actually, when I was last at CITA, I premiered a version of that talk. So this time, for those of you who might have been here, which is probably like 2 people, I'm doing a shorter version of that talk and adding on, which is a really theory part, and adding on more practical in the second half. And it's really a little bit of talk, hopefully 10 minutes for each half, and then more discussion. So please come and we'll have some fun.
Thank you.